The past few sections introduced matrix vector multiplication as a way to think geometrically about solutions to linear systems. We rewrote linear systems as matrix equations, AX equals B, and developed the concepts of span and linear independence. These ideas answered our two fundamental questions. Does a solution to that AX equals B equation exist? And then, if a solution exists, is it unique? Matrix vector multiplication can also be viewed as a function, like we would in, a function as we would think about like in a calculus class. It's a little bit different here, and we'll talk about it, but kind of the same idea. A matrix takes a vector as an input and produces a new vector as an output. These functions are called matrix transformations. They allow us to describe important geometric operations such as rotations, reflections, and transformations used in a variety of applications, including, for example, computer animation. And we'll take a look at that in this section. So we say that a matrix transformation associated to a matrix A is the function that assigns the vector x to the vector ax. That is, t of x equals ax. So we have our sort of, the name of our function here would be t, and we have our kind of standard function notation that we might be used to from a calculus class. However, sort of our input here, x, is a vector, and our output, ax, is also a vector. So we've got this function t that doesn't just take numbers to numbers like we might be used to for functions, but instead takes vectors to other vectors. And the way it does that is by multiplying the input vector by the matrix A. So let's take a look at an example. Suppose we have a 3 by 2 matrix A given here, 1, 1, 2, 3, negative 1, 2, and define the matrix transformation t of x equals ax. Let's just explore what it means to actually compute the value of this matrix transformation on a particular vector, in this case 2, negative 1. You could see that the input vector here is a vector in R2, which it would have to be for a 3 by 2 matrix, because our definition of matrix vector multiplication requires us to multiply a 3 by 2 matrix by a vector in R2. And so t of 2, negative 1 is defined as a times 2, negative 1. So we can write a times 2, negative 1. And if we recall sort of how this works, we're essentially taking a linear combination of the columns of the matrix A using the weights from the vector input here that we might call x, this 2, negative 1. And so this is equal to 2 times 1, 2, negative 1 minus 1 times 1, 3, 2. So the result here, we go through the math, 2 minus 1 is 1, 4 minus 3 is 1, negative 2 minus 2 is negative 4. And so you could see that the output here is a vector as well. In particular, it is a vector in R3. Okay. Again, same idea here, or same matrix here. We have this matrix transformation, and just to sort of review some of the things we looked at earlier, our inputs are going to be vectors in R2. The reason there is because again, our sort of definition for how we defined matrix vector multiplication would require that, since A has 2 columns, and the outputs are going to be t of x, and those are going to be in R3 because A has 3 rows. So the number of columns tells us the dimension of the input vector, and the number of rows of A tells us the dimension of the output vector. So if we were to use our kind of standard notation for functions, we have this function t takes vectors from R2 to R3. Generalizing this a little bit, if we have an m by n matrix, then the input vectors would be in Rn, and the output vectors would be in Rm. And so T would take vectors in Rn to vectors in Rm.